and my friend Jiminy will continue from this point.
So the simulation was run on a 3.2 gigahertz workstation of having 4 GB RAM at the facilities available at our engineering faculty here at KDU. And here you see the coefficient of drag is converging over time, which gives us a satisfactory level of convergence. The same can be said for the coefficient of lift also, which converges over time. Here we can see the results that we have obtained. Mainly we are looking at the coefficients of lift, drag and Mach number, moment. Because as we know in aerodynamics and as in fluid dynamics, we very much prefer to work with non-dimensional coefficients, which makes our solutions and makes our analysis much more easier. So the drag coefficient variation is shown here with the Mach number, and it can be seen that the drag diverges around 0.85 Mach, which is very prominent, especially in the transonic regime. This is a very common case with any aerofoil. But also when comparing these results with the two-dimensional case, we see that the rate of divergence is less than in the two-dimensional case, especially because in the three-dimensional wing, we see the three-dimensional relieving effect, which is very prominent in three-dimensional bodies. Here we see the lift coefficient variation with Mach number for two different angles of attack, mainly 0 degrees and 4 degrees. The reason why we could not run more simulations for more different angles of attack was mainly due to the limitations in computational power available to us right here at the university. So here we see that the lift slope is varying, showing a trend which is very prominent or very usual with any lift curve of a conventional airfoil. However, there's a slight difference is that for a given angle of attack, the finite wing has less lift at small angles of attack, since the three-dimensional wing, which is a finite wing, usually sees a lesser angle of attack. So the effective angle of attack for a given free stream angle of for a given angle of attack of the entire aircraft is less when we consider the three-dimensional finite wing. So also we see that the variation of lift is that the lift continues to increase as we increase Mach number, but that is at subsonic speeds. But however, as it goes into the transonic regime, the lift is destroyed. This is mainly due to the effects of boundary layer interactions with the formation of the incipient shock wave, that is the first shock wave that forms over an aerofoil. But however, as the shock wave moves with increasing Mach number, the shock wave starts to move along the wing, and the area which is affected by the boundary layer separation due to the interactions of the shock wave is then it moves to the backward of the wing, and then again it is able to produce some positive lift, which you see which starts again once it passes around 0.95 Mach. Here we see the moment coefficient curve, which is again varying with Mach number for two different angles of attack, and it remains at low Mach numbers. The moment coefficient remains negative, which shows that the wing is in a stabilized range, but again it continues towards the positive side with increasing Mach number. In usual airfoils, we have negative moment coefficients because the aerodynamic center or the moment around the aerodynamic center usually produces a negative moment around an airfoil. So again we have to remember that the specific aircraft wing that we have modeled usually cruises around 0.8 Mach, so it really does not fly in the transonic regime. So if it is to fly past the transonic or in the supersonic regime, then the designer will have to incorporate some means of overcoming this instability which is created somewhere around the transonic flow speeds. Here we see the static pressure contours of the three-dimensional wing. And you can see the stagnation areas which are shown in red color, which are very prominent, especially towards the root of the wing, which is attached to the boundary. This is the velocity profile, and again we see that you can see the cross flow which is happening, which is not present in a two-dimensional case. So in a three-dimensional wing or a finite wing, we see that there is some span-wise flow, where flow is going in all directions really, which gives rise to the creation of wing tip vortices, which you can see very clearly around the tip of the wing. I have to mention certain limitations that we had when we conducted this research. The main limitation was that we did not have certain data which we needed to generate a complete three-dimensional model of the wing-body combination, because as Mr. Bandara also mentioned, such data is not available through the manufacturer, and also we searched the internet, but we were not able to obtain any engineering drawings on the particular wing-body combination. And also we did not have any ability to get to physically or manually get any measurements to form the three-dimensional or the 3D model of this particular wing-body combination. The other restriction was the limitations in computational resources and power. So I hope that in the future, with the developments which are happening in the university, we will be able to generate more accurate results. So with that, we come to the conclusion of our presentation. So in this, we were able to analyze a three-dimensional body, a wing body, body rather, and we were able to analyze the flows physics. And this work will be a basis for many future work which we intend to do in analyzing the performance of the complete aircraft or the complete wing-body combination, and thereby we will be able to make certain recommendations to improve handling qualities or even certain design modifications as per the requirements of the users of the aircraft. Thank you very much.